Once again, exam 3 is on Wednesday. Right here, same time as usual. I should say same time as usual, but not right here. It'll be by email only. Send it back to the email address you get it from, just like last test. This will make sure the last section here. Yeah, so we said 9:10 through 10:05 last time, right? Well, mid 10:06, we're not covering that unless we get a little extra time at the end, which isn't likely this semester. Open book, open notes, open computer, no person may help you. Practice exams on D2L. We're going to go over those tonight. And any other problems you're interested in. Okay. What I might do is just go sort of straight through here to keep some of the same order, but really I'd like mostly to do the problems you're interested in. So is there anything in particular anybody wants to look at before we get off on the track here?
10.
Okay. The request for number 10, find the Maclaurin series for 2x e to the minus x. I feel like this one is not grungy like the other ones. By making an appropriate substitution in a known Maclaurin series and multiply. What I'm doing here is I'm thinking this is x times e to the u, right? If I think of x e to the minus 2x and call this u equals minus 2x, then the series for e to the u is 1 plus u squared over 2 factorial and so on. And now you just put minus 2x back in. This is 1 minus x times 1 minus 2x plus 2 squared x squared over 2 factorial minus 2 cubed x cubed over 3 factorial plus so on and so forth. And now multiply x in, you've got x minus 2x squared plus 2 squared x cubed over 2 factorial minus 2 to the third x to the fourth over 3 factorial and so on. So there's the Maclaurin series for x e to the minus 2x. Now remember that each Maclaurin series on any interval where it converges is unique. So there isn't any other series that would match it at all points on an interval like this. You can also do this from the sigma notation for this series if you prefer. But either way, if you do the sigma notation, you can convert it to here. And if you get it to here, you can see that if you wanted to write it in sigma notation, you could write this as sum n equals 1. Usually we start this at n equals 0. I'll say n equals 1. And since we start with x to the first, there's no constant term. And x just increases by 1 each time. 1, 2, 3, 4. So this is just x to the n. X to the 1 in the first term, x to the 2 right hand equals 1, 2, 3, 4. So power of x matches the term, and then 2 is to 1 power less, so it's 2 to the n minus 1, x to the n, and I should put one more thing in here. Because it goes plus, minus, we can call it minus 2. Well, let's call it minus 1 to the n minus 1, 2 trying to make this as simple as possible. Minus 2 to the n minus 1, x to the n over n minus 1 factorial. Everything here is always the n or 1 less, right? X to the n minus and 2 to 1 power less, and factorial to 1 power less. X to the n, 2 to 1 power less, and factorial 1 less. X to the n, 2 to the 1 power less, and factorial 1 less, and so on. So this comes out the sigma notation. So you can figure it either way and then find the other one. That was A. They use the Maclaurin series to approximate the integral. This is actually really useful in applications. A lot of times you get a solution that's an integral to an applied problem. Then you have to estimate the integral. This is one way that people do it. B says estimate the 4 decimal place accuracy. Integral from 0 to 0.5, 1 minus cosine of x squared dx. This is in the same vein as the first one, just one more step. The idea is to write a series for this. Think of this as u equals x squared. So I can say this is the integral from 0 to 0.5 of 1 minus, and then I'll put cosine x squared as, or cosine u is 1 minus u squared over 2 factorial plus u to the 4 over 4 factorial, etc. There's that. Now if I put u equals x squared, this is the integral from 0 to 0.5. Oh, the ones cancel nicely. I've got minus and minus is plus u squared, which is x to the 4th, over 2 factorial. Then minus u to the 4th is x to the 8th. Over 4 factorial. That was minus. Plus x to the 12th over 6 factorial, and so on. I just have to integrate that. And so the integral comes out to be, we integrate term by term, right? X to the 5th over 5 times 2 factorial minus x to the 9th over 9 times 4 factorial plus x to the 13th over 12 times 6 factorial, and so on. Plug in 0 and 0.5 and take the difference. So one of the theorems we have is that within a radius of convergence of a power series, you can integrate term by term to get the integral. So that's why I did here. I integrated this term to get this, integrated this term to get this one to get this one. Now, if I plug in 0, each of these terms is 0. That's the bottom. If I plug in 0.5, I get the following. You can also calculate derivatives term by term within the radius of convergence. What I've got is 1/2 to the 5th over 5 times 2 factorial minus 1/2 to the 9th over 9 times 4 factorial plus 1/2 to the 13th over to the 13 here, so that, sorry. 13 times 6 factorial, and so on. Now, what you notice about this is there's actually two theorems you can apply to get 4 decimal place accuracy, and I'll accept either one. We need error which is the absolute value of the remainder, less than or equal to get 4 decimal place accuracy, we get less than or equal to 0.5 times 10 to the minus 4. So 5 in the 5th place after the decimal place is 4 decimal place accuracy. So you can do that by requiring the error bound. Here's the error. I guess let's put it up this way: Rn of x. Well, let's put the bound on Rn of x, which was f to the n plus 1. M over n plus 1 factorial, absolute value of x minus x0 to the n plus 1 was the error bound on Rn of x. Well, m is the maximum absolute value of the n plus first derivative of c, or c between the point of expansion 0 and the point we're evaluating at 0.5. That looks pretty hard to compute, doesn't it? If I don't have to compute very many derivatives, I can do that. So this works. We can require this. I should have said less than or equal to 0.5 times 10 to the minus 4. It looks like I might just be able to take these first couple of terms and get it. This works, but we have to compute this, but this is awkward. I'll just say it works with difficulty. What's another way we can do it? If this one's hard. So you can compute like the 5th derivative and see what the bound is, see what the maximum value is. But what's easier is to say this is actually an alternating series. So this is by the remainder theorem for Taylor series and Maclaurin series. But you got to compute this nasty derivative. It's actually not too bad, but it's a couple product rules. Or by the alternating series theorem, because these alternate sign getting smaller and smaller going to 0, those are the hypotheses of the theorem. We just require the next term, 1/2 to the we want the next term, absolute value of the next term, less than or equal to 0.5 times 10 to the minus 4. So if I write this as sum n equals 0 to infinity, and these increase by 4, I can call this 1/2 to the 5 plus 4n. So if I put n equals 0, I get 1/2 to the 5th. I put in n equals 1, I get 1/2 to the 9th, and 1/2 to the 13th, and so on. And then this one down here is the same number that's up there, so this is 5 plus 4n. And then this is just, these increase by 2. That looks like n plus 2 factorial, right? You get, and then it's 0, you get 2 factorial, and then oops, 1. Be twice n plus 1 factorial, right? So if n is 0, you get 2. When n is 1, you get 4. When n is 2, you get 6. Yeah, so that'll do it then. There's the sigma notation for that. So we require 1/2 to the 5 plus 4n over 5 plus 4n times twice n plus 1. I don't want to make this too hard. I think I'm making it unnecessarily detailed. Try a couple of these terms. Try this one. 1/2 to the 13th over 13 times 6 factorial on the calculator. Is that small enough? If that's smaller than this number, then we can omit this term and just take these two. If it's not small enough, we look at the next one. So what you do is in the by the alternating series theorem, you take enough terms that the next term is less than 5 times 0.5 times 10 to the minus 4, and that will guarantee your error is less than that. All right, so let's try that. I think that one might be small enough. All right, so I'll take 0.5 to the 13th divided by 13 divided by 720 is 6 factorial. Yeah, that's way small enough. This is 20. 7 zeros, 1, 3. So if I take just these first two terms, that's enough. Maybe if I just take the first term, that's enough. So look at that one. 1/2 to the 9 over 9 times 4 factorial is 0.0. Yeah, this is plenty small. 2, 3, 4, 5, 6, 9, 0, 4, 2. All we need is less than or equal to 5 here. So this is small enough. We can just take the first term. Just hence the integral from 0 to 0.5 of 1 minus cosine x squared dx is approximately this first term, 1/2 to the 5th over 5 times 2 factorial, with error less than, with 4 decimal place accuracy at least. More than that, 1, 2, 3, 4, 5 decimal place accuracy. So this time just the first term is all you need to estimate. Comes out to be about 0.0031. Yeah. Anybody else want to suggest a problem? Now, that's kind of tricky, but it illustrates something important. Okay, well, I'm going to start doing the top next. And that one is actually the first subject, really. So let me not start at the top. Let me start let's start at 7a. What we did after the series with parametric equations first. Just find the equation of the tangent line to the parametric curve given by x equals 2 cosine t, y equals sine t, at t equals power 3. How do I find the slope of the tangent line? You just memorize this formula, really. It's easy to memorize. dy dx is the slope of the tangent line with this curve. Is this computed by dy dt over dx dt? We had that theorem we derived in class. So dy dt is cosine. Right, derivative of sine is cosine. Derivative of 2 cosine is minus 2 sine. So we get minus a half cotangent t, and then dy dx at t equals pi over 3 is minus a half cotangent pi over 3. We can figure that one out in the unit circle. Right? Pi over 3 is about that angle. So 30, 60, 90 triangle with this side square root of 3 over 2 and this side a half. There's a cotangent. The cotangent will be x over y, a half over square root of 3 over 2. All right, and now the 1/2 here cancels the 1/2 here, and you've got just minus 1 over 2 square root of 3 for that one. So that agrees with the back. I got something. I wanted to know. Let's see. Oh, it's finding a tangent line. I'm sorry. Tangent line. I found the slope of the tangent. So there's the slope. And then I have a point. Just by plugging in. X equals 2 cosine pi over 3. Y equals sine pi over 3. Cosine pi over 3, again looking at this as a half. Sine pi over 3, looking at the triangle, is square root of 3 over 2. If I have a point and I have a slope, then I can write the point slope formula. That's what you often do in calculus to calculate a tangent line. We find the point, we find the slope, write the point slope formula. So it's y minus y naught equals m times x minus x naught is the point slope formula for algebra. Gives, plugging in the point, x, 2 times a half is just 1, right? There's x naught. Now y naught is square root of 3 over 2. So it's y minus square root of 3 over 2 equals m minus 1 over 2 square root of 3 times x minus x naught, x minus 1. There it is. And then you usually simplify it into y equals mx plus b form. So if you add square root of 3 over 2 over, you have y equals minus 1 over 2 square root of 3x minus 1 over 2 square root of 3 plus square root of 3 over 2. There it is. So there's the slope intercept form. See what that looks like with our thing. I'm differing by a minus sign. looking at, I think this is the right answer. I wonder if have the wrong answer on back. We just changed the signs a little bit. It looks just like this, but this is plus, and this is plus. Otherwise, it's the same. I think I get this slope will look right. That's the difference. This one has the one on the answer on the back has positive slope, but I think I computed it right. dy dt is cosine t. The x dt is minus 2 sine t. I'll just drop my minus on there somewhere. Okay. So there's 7a. Now 7b. Oh, wait, this remainder term wouldn't have worked so bad since it turns out we only need one term. We could have figured it out pretty easily. B says find a second derivative, d squared y, oh boy, I can't write, dt dx squared at t equals pi over 3 for the same curve. How about that? Well, remember dy dx is dy dt over dx dt. We can do something just a little harder for the second derivative. We'll say d squared y dx squared is d dx of y prime, right? Well, y prime is just what we computed over there. And d dx, the derivative with respect to x, can be treated as dy prime dt over dx dt by that formula. So this is how you compute a second derivative, where y prime was computed by that formula. So y prime we found was minus a half cotangent t. So it's dt of minus a half cotangent t on top, and dx dt, derivative of 2 cosine t, is minus 2 sine t. Well, this looks like plus a fourth over sine t times derivative of cotangent t. So derivative of cotangent, remember, is minus cosecant squared. So this is minus 1 over 4 sine t times minus cosecant squared t. The minuses cancel, and we get plus 1/4 cosecant cubed t. That's the second derivative. Anywhere we were asked for in particular pi over 3. That's equal to pi over 3. So d squared y dx squared at t equals pi over 3 is then 1/4 cosecant cubed of pi over 3. Well, what's the cosecant cubed? To evaluate it, maybe it'd be easier to write it as sine. It's 1 over 4 sine cubed pi over 3. We already know sine of pi over 3, right? So over here, sine of the y coordinate is square root 3 over 2. This is 1 over 4 square root 3 over 2 cubed. Comes out to be 2 over 3 square root 3 if you do a little algebra then. And I'm off by the same minus sign. I probably just brought the minus when I do this key up. All right, any questions on that one? What this is supposed to illustrate is that if you have a parametric curve, x equals a function of t, y equals a function of t, you can still calculate the slope in the xy plane dy dx by taking this formula, dy dt over dx dt. It's very easy. Once you do that, you can do nice things like find a tangent line by using that slope to get the slope of the line and a point on the line, as we did here. Second derivatives are also possible by first taking the first derivative and then taking the derivative of that over dx dt. So I'll be able to do those kind of things on the test. That's what I want you to be able to do for derivatives and applications of parametric functions. Now there's a little more on parametric functions. We have arc length. That's number 9. Actually, let's do number 8 next. Here's another parametric thing. If x equals 2 plus cosine t, y equals 2 sine t going from 0 to pi over 2 pi, excuse me, eliminate the parameter t and sketch this. I want you to be able to do that also. On a lot of these problems, they're easier than this because what you can do is solve for t in one of these equations and plug it into the other one. This one, not so. It's a tricky one. But it's not too bad. You might recognize this as being something you've seen before. But if not, you can do this. When you have a sine and a cosine, or a tangent and secant, or a cotangent and cosecant, you can apply Pythagorean identity. Suppose I subtract 2 from each side here. Then I find x minus 2 is actually equal to cosine. Right? If I divide by 2 over here, I find that y over 2 is actually equal to sine. How can I eliminate sine and cosine of t? Well, I can square them. I know that this squared plus this squared equals 1 by the Pythagorean identity of trigonometry. So it must be that this squared plus this squared equals 1. So what I do is I subtract 2 to get cosine here, divide by 2 to get sine here, and then this squared plus this squared equals 1. So this is equal to 1 because of this. Now, how do I sketch this one? This should look like something you know. This is equivalently x minus 2 squared over 1 squared plus y squared over 2 squared equals 1. And that looks like an equation for what? X minus x naught squared over a squared plus y minus y naught squared over b squared. This is an ellipse, right? That's the standard equation for ellipse with a equals 2, b equals 1. Foci is centered at 2, 0 because it's shifted there. Vertical foci, since I should call this a, sorry, since the bigger number a is under y. So vertical foci, and I can sketch it as easy as drawing an oval, right? I simply go over to 2, 0, the center. Then the semi-major axis is 2 in the y direction. I go up 2 and down 2, and those are the ends of the semi-major axis. Semi-minor axis is 1, so I go 1 each in the x direction, and I have this oval. There it is. And you can compute the foci if you're interested. All I asked for was that sketch. On these sketches, you just want to eliminate the parameter and recognize an equation. That's the idea. Let's see. Now let's look at 9. The other thing you can do with parametric curves is look at the arc length or the arc length parameterization. Suppose I give x equals 2t to the 3 halves y equals 4t, and let t run from 0 to 1. What's the arc length? You memorize this formula. It is the integral from a to b, square root of dx dt squared plus dy dt squared. So you have to memorize this one. A and b are where t starts and ends, so it's integral from 0 to 1. Square root of derivative of x is twice 3/2 t to the 1/2. It's just 3t to the 1/2. Derivative of y is 4. I have to be able to do this integral. Typically, this becomes a very difficult integral. However, for the test, you can expect it to be well with it that can be done. This is integral from 0 to 1 square root of 9t plus 4 dt. We can do this integral. I expect to be able to do these ones. It is all right with me if you want to go online and use that symbol lab calculator to do this, or with a Mathematica Wolfram widget, Wolfram Alpha, I guess they call the main program, Wolfram Alpha, to do these if you want. But I would really like to be able to do these by hand too. U equals 9t plus 4. The hint is, as a function of a function, try letting u be the function that's inside. Then I have to also replace dt in favor of du as the derivative of this dt. Well, it's 9 dt. My derivative of this is 9. So I can divide by 9 and say 1/9 du and replace dt. And this becomes the integral of 1/9 square root u. du. Right? Replace dt with this and this with u. And now u doesn't go between 0 and 1. When t equals 0, u is 9 times 0 plus 4 is 4. When u is 1, u is 9 times 1 plus 4 is 13. So the integral now goes from 4 to 13. Well, this is an easy integral. The 1/9 comes out. Integral of u to the 1/2 is u to the 3/2 over 3/2, or 2/3 u to the 3/2. Then I need to plug in 4 and 13 and take the difference. So I have 2/27 times 13 to the 3/2 minus 4 to the 3/2. 4 to the 3/2 reduces to 8, right? Square root of 4 is 2, and then cubed is 8. 13 and 3/2 can be written as 13 square root 13. So if I can erase my substitution thing here, 1/9 du equals dt. I can write this a little simpler as 2/27 times 13 square root 13 minus 8 by algebra. Suppose I said this. Another thing we did was the arc length parameterization. This is not on the homework on the list here, but I might ask you this. Find the arc length parameterization of the curve x equals 1 plus 2 sine t, y equals 2 cosine t. I already know what this curve is, actually. See what it is? It's actually a circle. If you eliminate the parameter, x minus 1, if you subtract 1 and divide by 2, you got x minus 1 over 2 is sine t. This one, if you divide by 2, y over 2 is cosine t. So you have that x minus 1 over 2 squared plus y over 2 squared equals 1. Sine squared plus cosine squared equals 1. Multiply by 4, and you've got x minus 1 squared plus y squared equals 2 squared. It's a circle of radius 2 at the point 1, 0, right? X squared plus y squared equals 2 squared would be a circle at the origin. If I replace x by x minus 1, that shifts it over to 1, 0. So now what's the arc length parameterization? You might be able to guess it if you've got a good intuition at this point. But here's what you do for, so this is an aside, not requested. We can sketch it. The whole thing's not requested here, but we can now sketch it. We go over to the point 1, 0, sketch a circle of radius 2. It's supposed to be centered there. Oh, well. All right, 1, 3. But the arc length parameter S of t is defined as the integral from a reference point where the arc length starts, t0, any point you want where you want the arc length parameter to be 0, to t, of the square root of dx dt squared plus dy dt squared dt. If you think about the arc length formula, the arc length parameter is just the arc length from t0, or a, whatever you want to call it, to t along the curve, right? This is the arc length from here to here. So for this one, if I choose t0 equals 0, just to start, it says, again, I didn't say relative to particular t0. So let's choose t0 equals 0 just for simplicity. And this becomes the integral from 0 to t of square root of dx dt is 2 cosine t. dy dt is minus 2 sine t. And now you've got integral from 0 to t, the square root of 4 cosine squared plus 4 sine squared. The square root of 4 can be factored out and pulled out of the square root as a 2 on the outside, right? 2 on the outside is equivalent to multiplying by 4 on the inside, so I'll simplify it like that. Well, what's cosine squared plus sine squared? By trigonometry, it's 1, yeah. So this is just integral 2 dt is 2t. How about that? Now, if s equals 2t, by the way, this arc length is always an increasing function when the as long as dx dt and dy dt are never both 0, as long as you never stop along the curve so that these are both 0, this will be an increasing function, so you can always inverse this and write t as a function of s. So this implies that t equals 1/2 s, since s equals 2t, t equals 1/2 s. Implies that you can write the original equations here, x and y as functions of s. X equals 1 plus 2 sine, and I replace t with 1/2 s. Y equals 2 cosine, and replace t with 1/2 s. There it is. This is x as a function of arc length s. If you put in s equals 4, it's exactly 4 units along the curve from the point where t was equal to 0. And now where s is equal to 0. So there's arc length parameterization. You take the arc length integral and just go from any reference point t0 to an arbitrary point t. And that becomes the arc length as a function of t. And if you invert that to solve for t as a function of s and plug it back into the original parametric equations, you've got what's called the arc length parameterization, because now x and y are functions of arc length s. Like the little wheels you push along there to measure a 5K race or something. Right, this tells you exactly how far you are along the curve as you go. All right. So that's that's all on parametric curves. Now we do the application of parametric curves to polar coordinates. There is one more parametric curve, number 2. If you want to do that one, we can do that one too. Maybe I'll go ahead and do 1 for now. Think about it if you want to see 2. Find the area of one petal of the rows r equals 2 cosine 3 theta. It does help to remember that if n is odd, you get exactly n petals. For a cosine n theta is a rows, and a sine n theta also is a rows. This is a 3-petal row. Since n is odd, if it was an even number, it would be 2 n big number petals. That's sometimes a hint, just making sure you're doing this all right. What you want to do is find where a petal begins and ends. You make a table. Where is cosine equal to 0? That's where a petal will start, is where the radius, right where you're at the origin. So let's see, cosine is 0 when theta equals pi over 2, for instance, right? So I need 3 theta equal pi over 2. I could pick theta equal pi over 6. Right? Then r equals 2 cosine 3 theta will be 2 cosine 3 times pi over 6, but cosine pi over 2 is 0, so that will start a petal. Then you have to ask yourself, when is the next time that cosine is equal to 0? That's where the first petal ends. This is where the first petal begins. What's the first time after pi over 6 when cosine is equal to 0? Well, cosine is equal to 0 next when this is 3 pi over 2. So now we need